and welcome friends. Today we are going to start with the chapter of relations and functions. This is going to be an amazing ride because relations and functions, this particular chapter forms the basis of the entire calculus, and this is going to be a very crucial chapter not only for calculus but for many other things. And this particular chapter indeed will connect with many real life examples, so to say. Now, talking about relations and functions in a very simplistic way, there are many things that in the general day-to-day life you use which are actually functions and naturally go unnoticed, right? So they can be calculators, there can be simple functions in mechanical world, or for that matter in the electronic world. For example, even in Delhi nowadays there's this odd even scheme going on for reducing air pollution, right? So even there we have a function that is going on. Basically the thing is, every odd date, on every odd date we are using odd cars, and on every even date we are using even cars. Indeed, that is a function as well, right? That's basically a rule. So that is the key word over here. Relations and functions are nothing but a correspondence between a particular input to get a desired output. So let us try and write this in a simplistic way. There is an input, and that particular input, there is a rule over this input which gives you an output. This rule, this word rule, has many other variations of it. We can call it a correspondence, we can call it a relation, we can call it a function. Although about these two particular words, relation and function, we are going to learn in more detail gradually in the chapter. But in this particular introductory video of this chapter, let's try and understand what is this all about. It's basically about this. You have an input, you insert an input, and depending upon this rule, you have an output. Let's try and take a very simple example based on the very thing that we talked about, the even odd scheme, right? Now, I have these two pens, I have these two markers. One of them is a pink one, one of them is a blue one. Let's try and create a rule. Let's have a rule that if there is an odd number popping up, I'll raise the pink marker, and if there is an even number popping up, I'll raise the blue marker. Let's have some examples. Here is the first number. Yes, this particular number 4 is an even number, so I'll raise my blue marker. Now the next number that pops up here is 13. Now that indeed is an odd number, so I'll pick up this marker. The next number that we see over here is 5. Again an odd number, so I'll pick up this particular marker. Now the next number is 10, and that is an even number, so I'll pick up the blue marker. So as we saw, this was a very simple example of a function, of a rule basically, right? The rule here was that if we have an odd number, I'll pick up a particular marker, and if we have an even number, I'll pick up the other kind of a marker. So basically, depending on this rule and depending on the input was processed in my head, and accordingly I gave you the output. And that is what the role of a function or a rule is. And this rule, humans have created many kinds of machines, right, to process these inputs according to a rule to give you a desired output. So on this note, on this very idea, on this very concept of a machine, let's try and build one. Here's one machine that we have, and as you can see, this over here is basically the input area. You are going to have input elements from here, and the machine is going to process according to the rule that we are going to define, and it is going to give you outputs, right? So let's try and have another example. This particular machine for us is basically hovering around a rainbow. So as you can see, on the very front area of the machine, we have the image of a rainbow, and as we know, we have 7 colors in a rainbow. Before going to numbers, which is actually the key area of this particular chapter, let's try and dance around few colors so that we grasp the idea of what input output machine or a function is, right? So let's try and define this machine with respect to the rainbow in such a way that we are going to insert spheres of a particular color, right? So basically, let's say if I am inserting a orange colored sphere over here, what is going to happen is the machine is going to process that input and give you an output in this particular fashion. For every sphere, every colored sphere, every nth colored sphere from the start, the machine is going to give you an output which will give you the sphere which is nth from the end. So this is how the rule is. First, let's try and understand the rule. What the rule suggests is, if I have a sphere of a particular color and that color is nth color from the start, then the machine is going to give you an output of the nth color from the bottom of the rainbow. Now we know a rainbow, now we know the order of colors in the rainbow. If I am inserting an orange colored sphere, right? Now the color orange in a rainbow is the second color from the start, right? So if I'm inserting an orange colored sphere, the output should be another sphere which is second color from the bottom. And as we know the 7 colors of a particular rainbow, it is nothing but red, orange, yellow, green, blue, indigo and violet. Now, since we have the second color from the start, we are naturally going to have the second color from the bottom, which is indigo. So the orange colored sphere which is getting inserted as an input is going to give you an output of an indigo colored sphere. Now let's take another example with the same particular rule. If I am inserting a red colored sphere, it naturally is going to give you a violet colored sphere. Likewise, if I insert a yellow colored sphere, it is going to give me a blue colored sphere. And if I insert a green colored sphere, which is the 4th color from the top, it will give me the 4th color from the bottom, which is indeed going to be the green color again. So if I am inserting a green colored sphere, I am getting a green colored sphere out. So now, likewise, another example would be if I am inserting an indigo colored sphere, it has to give me an orange colored sphere. So a very simple example again, here we were playing around with colors, but what we understood here is every machine, every rule, every law will give me ordered pairs. An ordered pair is basically nothing but a pair of an input and an output. Like as you can see, these are the ordered pairs that we have over here. And this is going to naturally give me 7 different ordered pairs because there are 7 possible inputs in this particular case for the rainbow, because the rainbow has 7 different colors in it. So right, so this was an example of a machine which has inputs and outputs involved in it. Now what we understand is the rule, right? The rule has many different words, as we call it a correspondence. We have another word called relation, another word called function, another word called law. All these things basically signify the same thing, that we have an input and that input is processed according to this rule, according to this law, according to the machine that we create, and hence get a desired output. Now, since at the start we were talking about examples, real life examples of functions and relations, and I happen to mention about calculators, right? Now, as far as I remember, the calculator initially in the history was developed by Pascal. Pascal, the great mathematician, he was indeed very famous for having many discoveries, as you might have gone through in physics as well. Now, the story goes as such. Mr. Pascal's father was basically an accountant. He used to do the work of collecting taxes, which indeed involves a lot of calculations. And one tiny mistake is definitely going to affect a lot of things, right? So to solve his father's problem, what he decided is to create a machine, to create an algorithm which basically simplifies all this calculating process, and then started the process of creating the first calculator, right? And he started this process in 1642 and came up with the calculator in 1645. Although to create an economic version of that calculator in those times was really very difficult, because the mechanics was not very much developed, evolved in that age, but certainly it helped giving the giving the output, making the calculations a hell lot easier. The point here is to understand that the making of a calculator is based on the concept of a function. And what the function basically is, that if you have to perform a particular operation, let's say perform a particular operation of a multiplication, of a division, of squaring a particular number, of cubing a particular number, then you simply have to press one particular button and then it will directly give you an output. You don't have to worry about how does the operation is performed. So again, that is a machine. You are inputting something, and according to that particular button, according to that particular machine, your desired output is coming, right? Let's say if you want to find out 12 raised to 4, right? So in actuality, where assume that you don't have a calculator, what you will do to find out 12 raised to 4 is multiply 12 4 times. So basically what you'll do is 12 into 12 into 12 into 12, right? So 4 times you'll multiply the same particular thing. Now what the calculator does is it performs this particular application at the click of a button. So what you have to do is simply insert the input 12 and simply press that particular button, which indicates the kind of function, the kind of rule that you have to perform, which will be x raised to 4. So simply 12 raised to 4 will be the output that you desire in the matter of milliseconds. So that is what the aura of a calculator is. So basically the point here being, the calculator indeed is a machine which is a combination of many rules, many functions. You just have to insert an input and get your desired output depending on a particular rule. Now, I guess you must have understood the basic concept of functions, relations, the input-output thing which is based on a particular rule. Let's take a couple of more examples to make this idea concrete before we move on to things like sets. What are sets? What are relations? And then actually going into the details of functions, where we'll be taking a lot of examples related to numbers. We'll be talking about the x, y axis and different functions in the form of y equal to f of x, where we'll be actually plotting a lot of graphs, playing around with them, understanding a lot of concepts like odd functions, even functions, many one functions, inverse functions, periodic functions, and so on. So this ends the introductory video, my friends, for the chapter of relations and functions. I hope you had fun. Now we are going to start with sets. After that, we are going to learn about relations, and then we are going to hop onto functions. But one thing we need to understand, that here we had a mixture of word examples and a numerical examples as well, and gradually we are going to use the same example of a machine to understand different aspects of functions, but at the same time we are also going to take numerical examples to correlate and understand a particular idea, a particular concept when it comes to functions. Hello friends, after seeing the introductory video of this chapter of relations and functions, now first of all we are going to start with the concept of sets, so that we can learn what is a set, what are the different aspects of set, and then how sets are going to be used to understand relations and functions in a broader sense of view. So let's first understand what a set is. A set, in a very general definition, is nothing but a collection of elements. For example, if I take a very simple example of vowels in the English alphabet, right? We know that we have 5 vowels: A, E, I, O and U. Now, if I write them in this kind of a way, right? Now, in this ellipse of a sort, if I write these elements form this set, which I can call as the set of vowels in the English alphabet, right? So this is how we define a set. Now, when we talk about sets, there are two basic definitions, two basic distinguishing elements. The first thing is sets which are made up of well-defined elements, and sets which are made of not well-defined elements. Like, as we took an example, vowels of English alphabet is a well-defined set, right? Because we know that A, E, I, O and U are the 5 elements, and the only 5 elements that are in this particular set. So I can write this set as, let's say I write this set as V, and then V is equal to this is how I write a set, and it can be represented in this particular way as we have seen. Now this is a well-defined set, as I said. Like this, there are many well-defined sets. For example, another well-defined set would be the list of odd numbers less than 10, odd natural numbers less than 10. Then we have 1, 3, 5, 7 and 9 as the 5 elements. On the other hand, if I say list of odd natural numbers without any other condition, then you would realize that this is an infinite set. But still, this is a well-defined set because we have a particular proposition for that set. For example, to take a general example, rivers in India is also a well-defined set, because I know all the rivers which can, or if not, we can still figure out all the different rivers which flow in India, and then it becomes a well-defined set. Now, on the other hand, if we want to know what an example of a not so well-defined set is, then we can take the example of collection of stars. Now, this is not a well-defined set because we don't know all the stars which are there in the universe. The list is actually endless, but at the same time, it is not well-defined because you would not be knowing n number of stars which are existing. For example, I can take another example like NRIs living in United States. Although now the proposition is all the non-resident internationals who stay in this country of United States, that is the condition applicable there, but we don't know how many NRIs are there and from which all countries are coming, so it's not a well-defined set. So that is how these two definitions, distinguishing elements, so not well-defined sets. So if the condition is a defined one, the definition, the proposition is a well-defined one, then it is called a well-defined set, and on the other hand, if it is not so well-defined, it is called a not well-defined set. So these are the two basic distinguishing things when we start off knowing what a set is. Now after that, there is one thing that we should know while we represent elements. Generally, sets are written in by using the capital letters of the English alphabet. Like here, I have used the letter capital V to represent the set of vowels in the English alphabet. Now, here I can write that E, right? E is an element of this particular set V. So how I can write this particular thing is E belongs to the set V. Now, as I said, we always write the name of the set in terms of capital letters. So V is the capital letter representing the all the vowels. So E belongs to V. As same as this, I can write A belongs to V, I can write I belongs to V, I can write O belongs to V, and I can write U belongs to V. All these will be these small letters, and this will be the capital letter will be representing the set V. Now, this is for a particular element to belong to a set. On the other hand, I can write, let's say C. Now we know the letter C does not belong to this particular set. Now to represent that, we will write it in this fashion, that C does not belong to the set V. So this is how we write. This signifies that this element belongs to this set, and this symbol signifies that this particular element does not belong to this set. So these are a few basic things that we need to know. Now after this, let's move on to the next thing that we need to learn, different forms in which we can represent sets. The first one is the roster form, or as we call it, the tabular form. Now this is the very way in which we wrote the very first set over here. So this is the roster form where we use the two braces over here, and all the elements will be inside these two braces. So this is this is how we write it. Vowels in English alphabet is written as V is equal to, as we have written there. Now let's take another example on this note. As we talk about numbers, even natural numbers less than 12, let's say. Now let's mark this one as, let's say, capital E. And this will be equal to, now natural numbers, so they begin with 1, and the condition is that these numbers have to be even. So the set will be 2, 4, 6, 8, 10, 12. No, I can't put 12 because the condition is that these numbers have to be less than 12. So the set ends over here, and this is how we represent this particular set with the condition in the roster form. Right? So you can have different kinds of sets here. You can have names as well. For that matter, let's say you want to write metro cities in India. Let's have this set as capital M. Right? Now you can write Mumbai, Delhi, Kolkata, and Chennai. So these are the 4 metro cities you can write in this particular set, although you can involve a few more cities as well. That's totally up to you. But the whole motive here is to understand the roster form, the way things are written, the way sets are represented. Now let's move to the second way, the second form, which is called the set builder form. So let's understand what the set builder form is. Now again, all these sets can be written in the set builder form as well. It's just that the way in which they are represented is slightly different. So let's see how we are going to write it in the set builder form. Let's use the very first one itself. So now this set V will be written as V is equal to curly braces here. Then we will have X, right? X is a general alphabet which represents the condition that we are going to write further. So first we need to start this with the braces. Then we have the general alphabet. This alphabet can be anything. It just represents the general element which is going to satisfy the condition which comes after this. So it is braces, X, the general element with the 2 dots over here. This represents that this element follows this condition, that it is a vowel in English alphabets. So now as you are seeing, we are not writing all the elements, but we are specifically writing the condition which is going to frame that particular set. So this is how we write that. Now let's try and write the same for the second one. This is going to be E is equal to, now you can use any general element. This time let's use Z. So Z, now one thing that we missed out here is after this element X, when we put two dots, we need to just write here that X is an, or X is a vowel in the English alphabet. So likewise, you will understand this here. This will be Z less than 12 and an even natural number. So as you can see, we have written the condition over here specifically on the general element Z, which signifies the set E, right? So this is how we write that. Now again, for this particular set, we would have to write the condition that a particular element A is nothing but a city, a metro city in India. That is how it works. Now on this note, I want to put forward a few conditions, a few general conditions that we have in the roster form, that we have seen here. The first thing that we should understand is that the elements that we write in this particular form, in this particular set, the order is not important. So what it means here is this particular set can be written as E, O, I, A, U as well. This set and this set is going to be absolutely same because the elements inside the set are same. It's just that they are flipped in a particular way. So the formation, the way in which it is written, the order is immaterial. What is important is the elements. The elements need to be same for the set to be same. The second thing that we need to understand is, here let's just write that thing. Order is immaterial. Now the second thing that we need to understand here is that elements cannot be repeated in a particular set. So if I want to write letters in the word, let's say banana. Now I have particularly used this particular word because there are many letters which are repeating, and let's say F is the set which represents that. Then I'm going to write B, A, N, and that's it, because I will not write A again because then it will repeat the element which is there already here. I cannot write N again because N is also written once, and likewise I cannot write the last letter A as well. Point being, elements should not be repeated. These are the two major conditions that we need to remember while we write a particular set in the roster form. So now, after understanding a bit about the different forms in which sets can be represented and a few conditions on those, let's take this thing a bit further and know something about subsets. Now, subset, as the word itself suggests, is a smaller quantity of a larger set, right? Subset. So as the word suggests, as I said, so in this particular set, V is equal to A, E, I, O, U, or as we have written E, O, I, A, and U. These are the 5 elements. A subset would be basically another set which is smaller to this set. So let's say if I have a set V1, right? V subscript 1, and if I have 2 elements out of this, E and O, right? So if V1 is equal to E and O, only these 2 elements, then V1 will be called a subset of this particular set V. Now let's have a diagrammatic understanding of this. Let's say we have this particular rectangle over here. Now this, what we are going to learn, is called Venn diagrams, which are going to be constantly used in this particular section to understand different kinds of concepts that we are going to study further. So this is a rectangle. The Venn diagram of this set V is what we are going to understand. Now this rectangle will represent the universal set. A universal set is something which involves all the elements in a particular situation. So for this, let's say that V is itself the universal set. So we have the 5 elements, as we can see, A, E, I, O, U, and as I said, V1 will be the subset. So these 2 elements, E and O, they are forming another small set which we are calling as V1, and we are involving both of them in this particular circle. So that circle represents the set V1. So let us just write that down. So V1 is equal to E and O. These are the 2 elements that V1 has. Now likewise, if we have another set V2 which has I, A and U, so we have another subset V2 which has the 3 elements I, A and U. Likewise, we can have another subset V3, let's say, which has 4 elements apart from E. So basically V3 has O, I, A and U, and that becomes V3. No need to have that in a circle as such, but what we need to understand is a subset is basically a smaller version of all the elements that we have, right? So that is why we call this a subset, and this concept of subset can be applied to any set that we learn, right? So now in this 2, 4, 6, 8 and 10, 2, 4 and 6 will be another subset of this set E. So that is how subsets work, and we have understood how Venn diagrams are represented. Any set is represented in Venn diagrams. These Venn diagrams are going to be utilized in the further concepts, as I said. Now on this note, after understanding this, let's understand what are how do we calculate the number of subsets for a particular set. So a very important thing, number of subsets. Now after understanding what subset is for a particular set, let's say we have a set and the number of elements in this set S is equal to n. Now this is the way how we write number of elements in a particular set, right? N, round bracket, we write the set name, as we can see here, S is the name of the set defined by a particular condition. There are n elements in this. We don't need to worry right now what is the condition and what are the elements. The important thing we need to understand is there are n elements in this particular set, right? So we want to figure out how many subsets can we form with this particular set, right? So the thing is, a subset is basically a smaller set, or for that matter a subset can also be the original set as well. The only difference is if I involve all the elements in a particular set to form a subset, then that is called an improper subset. So basically another I can say that E, O, I, A, U is also a subset of V, but that is an improper subset because it has all the elements. A proper subset is something which has at least one element less than the elements that the original set has, right? So that is the difference between an improper subset and a proper subset. Again repeating, a proper subset is something which has at least one element less than the original set. So if I have E, O, I and U, 4 elements apart from A, then that will be called as an proper subset. At the same time, if I have only the element I, then still that would be a proper subset. If I have no elements from this, then still it will be a proper subset because the condition that at least one element less from the original set is satisfied and hence called as a proper subset. So we understand the difference between a proper subset and an improper subset. Right? And generally this is how we represent subsets. This signifies that A is a subset of B. So likewise here, as I said, V1 was nothing but E and O. So V1 is a subset of V. This is how we write that. Right? Now what this signifies is, it signifies the proper subset. It says that A has at least one element less than B, right? And B has all the elements what A has. So basically A is the superset of, rather B is the superset of A, because B has all the elements which A has, but A has at least one element less than B. Let's try and understand this from the Venn diagram itself. This is the universal set, let's say. Now we have a set B over here, right? And set A is inside the set B. So from the diagram, it's pretty clear that all the elements inside set A will be also the part of all the elements of the set B, in fact. And there will be a few elements in set B which are not the part of set A, and that is how proper subsets are defined. And that there was an example that we also saw that V1 is a subset of V, so there will be a few elements in V which are not a part of V1, hence making it a proper subset. Now an improper subset would be when A and B are absolutely equal, when A has all the elements that B has and vice versa, so that will be an improper subset. Now coming back to number of subsets. Number of subsets is in fact all the number of subsets that can be formed, the proper and the improper ones as well. Now coming back to this general agenda that we had here, we have a set S which has n elements inside it. This is how we write the number of elements in a set. Then how many subsets can be formed? Now we learned that subsets can be formed by picking up right from 0 elements to n elements. So now the thing is, let's understand this from the point of view of permutations and combinations. The chapter that we have learned there, we had used the concept that to choose R elements from n, there are NCR ways, right? So to choose 0 elements, there are NC0 ways. Now to choose one element out of n, we have NC1 ways. To choose 2 elements, we have NC2 ways. And like that, to choose all the n elements, we have NCn ways. Now the total number of subsets that can be formed in this way is nothing but the addition of all of these, right? Because we can form a subset of this set by choosing 0 elements out of n. We can form a subset by choosing 1 element out of n. Likewise, we can choose by choosing 2 elements out of n, and so on. We can also form a subset by choosing all the elements out of these n. Now, since we have learned in the chapter of PNC that this is nothing but 2 raised to n, and how had we learned that? We had learned that by using the formula 1 plus x the whole raised to n is nothing but NC0 x raised to 0 plus NC1 x raised to 1 plus NC2 x square and so on plus NCn x raised to n, and then substituting x as 1, we get this as 2 raised to n, and hence the total number of subsets that can be formed for a set which has n elements is nothing but 2 raised to n. So for this very example, the total number of subsets that the set V can form is nothing but 2 raised to 5, and 2 raised to 5 is indeed 32. And we can see that by having this 5C0 plus 5C1 plus 5C2 plus 5C3 plus 5C4 plus 5C5. This is going to be 2 raised to 5, which is equal to 32. So 32 number of subsets are going to be formed with this particular set. Simple example, 5C0 is indeed 1. There is only one subset which is, as we call it, the null set. There is only one set where we can have no elements selected from this. 5C1 is going to be 5 because I can form a set which has only one element E, which has another subset which has only one element O. Likewise, we can have 5 different sets. So 5C1, which is 5. Then 5C2 is 10 because we can form 10 different subsets by picking up or choosing 2 elements at one time. So EO is 1, EI is 1, EA is 1, EU is 1. We have 4 already. Then we have OI 5, OA 6, OU 7. Then we have IA 8, IU 9, and lastly AU 10. So likewise, we have chosen 2, 5C2 is 10, and likewise if we carry this process, this is what we get. And lastly, as you can see, 5C5 is basically choosing all the 5 elements out of these 5. There is only one possibility, select all the 5. So we get one improper subset. These are all proper subsets, and the total is 2 raised to 5 equal to 32. And if the question asks how many number of proper subsets a particular set can form, that would be simply 2 raised to n minus 1, because always there is going to be only one improper subset which you have to subtract from 2 raised to n to get the total number of proper subsets. So on this note, my friends, we'll conclude the understanding of number of subsets, how to calculate number of subsets from a particular set which has n elements in it. In the next slide, let's understand different kinds of subsets and the further concepts after that.